We're going to look at calculating the line currents of an unbalanced delta load with different power factors and different impedances in each phase. Here's an example. We've got a 600 volt delta connected load. In phase A to B, we've got a coil that has an impedance of 15 ohms at a 0.866 power factor. In B to C, we've got a coil capacitor in series that's giving us an impedance of 40 ohms, and it ends up being at a 0.7070 lead. So a power factor 0.707 lead. And then in C to A, we've got a resistor of 30 ohms. So given power factors like this, we need to convert that over first off to the angle. So the current is going to lag the phase voltage by 30 degrees. And for IA to B, it's going to lag phase voltage A to B by 30 degrees. The current in B to C is going to lead the phase voltage B to C by 45 degrees. And the current in C to A, well, it's going to be at 0 degrees to phase voltage C to A. Because it's a resistor, current stays in phase with voltage. So I'm going to start calculating my phase currents. And so first one I'm going to do is IA to B. So IA to B will be voltage A to B, which is 600 volts divided by its impedance, ZA to B, of 15 ohms. That comes to 40 amps. Now, because there's a 30-degree lag, we have to subtract that from 360, because VAB is plotted at 0 or 360, same point. So I'd have to plot that at 330 degrees. So there's IA to B, down 30 degrees from VAB, 40 amps. Now, while I'm looking at IA to B, I know that vector or phasor IBA is going to be the exact same magnitude. It's the opposite phasor, but it's going to be 180 degrees from wherever IA to B was. So IA to B was at 330 degrees. I'm going to find the opposite to that, so 330, subtract 180, it comes to 150. So I'm going to go ahead and plot that out. IB to A is 40 amps at 150 degrees. Now I'm going to calculate my next phase current, IBC. That would be voltage B to C, so phase voltage B to C, divided by Z B to C, so 40 ohms. That comes to 15 amps. Now in this case, current will lead the phase voltage. So it's going to be 45 degrees ahead of voltage B to C. Voltage B to C occurs at 240 degrees. So I'm going to take 240 degrees, I'm going to add 45. I'll have to plot IBC at 285 degrees. So adding degrees, 240 plus 45, IB to C is 15 amps at 285. Okay, the opposite vector of IBC is IC to B. IC to B is the same magnitude, but it'll be 180 degrees from wherever current IBC was. IBC occurred at 285 degrees. So I'm going to subtract 180 degrees from that, and so I'll have to plot current IC to B at 105 degrees. IC to B is 15 amps at 105 degrees. The next phase current I can calculate is IC to A. IC to A is our phase voltage CA divided by our impedance in C to A. In this case, it's just purely resistive. 600 volts divided by 30 ohms is 20 amps. So it's going to occur right where voltage C to A occurs. So it'll be at 120 degrees. So we'll plot that in there. IC to A, 120 amps. So it's at 0 degrees to our voltage C to A. So it is right at 120. I can now find the opposite phase current of IC to A, IA to C. It's the same magnitude, 20 amps, but it is exactly opposite from where we plotted IC to A. IC to A was plotted at 120. So 120 plus 180 will be at 300 degrees. IA to C is equal to 20 amps at 300 degrees. Let's plot that out. IA to C, 20 amps at 300 degrees. So we can now start adding these vectors up to get our line currents. As a review, we have to use this method every time we deal with an unbalanced circuit. And this is the definition of a balanced circuit, same impedance, same power factor in each phase. This is definitely not balanced. So if I want to calculate line current IA coming in right here, I know that that line current comes in and it splits, and it's going to be this vector sum of current IA to B and A to C. So IA will be equal to IA to B plus IA to C. That would be 40 amps at 330 degrees plus 20 amps at 300 degrees, IA to C. That comes to 58.2 amps at 320.1 degrees. Because we ended up in the bottom half of our phasor diagram, our calculators will express it as a negative angle. So I'll have to take 360 and subtract 39.9 degrees is what will be in your calculator in order to give it a positive reference. And that'll be 320.1. So if I plot that out, IA is right here, 320.1, 58.2. Okay, so let's go ahead and calculate IB now. If I want to know what IB is, current would come in on IB and it splits. And it's going to be the sum of phase current of IB to A and IB to C. That will be these two. So IB B is equal to IB to A plus IB to C. IB to A is 40 amps at 150 degrees plus IB to C 15 amps at 285 degrees. That comes to 31.2 amps at 169.8 degrees. We'll go ahead and plot that out. And there it is. IB 31.2 at 169.8. Our last line current is line current C. So if I want to know what IC is, line current IC, current would come in, get to the junction, and there it would split. And it would make up the sum of the phase current IC to B plus IC to A. As you see, that's these two. Okay. IC is equal to IC to B plus IC to A. That would be 15 amps. IC to B is 15 amps at 105 degrees plus IC to A 20 amps at 120 degrees. That comes to 34.7 amps at 113.6. Let's go ahead and plot that out. So right there, 34.7 at 113.6. I hope this helped you out, and we'll see you on the next video.